detailed logic behind the subject theory of computation, or we will call it as automata theory and formal languages. Okay, so today is the class. We are going to first learn about the machine. Okay, so today we are going to learn the first machine. So then you may able to imagine, sir, you are talking about machine. Then that machine will look like as my current knowledge about computer machine. Whether that machine also have a CPU, that machine also have a memory, that machine also have an input, that machine also output, and that is also physically available. Except the word physically available, that machine also will have all the component as like a computer. That's why now I wanted to give you a one more definition about these machines. This is not a practical machine. That's why it is not physically exist. Then what type of machine is this? This is the theoretical machines. So physically not exist, and in the theoretical format, in the written format, this is exist. So this is what the first level understanding is supposed to have about those machines. That's why the general or one line definition of this machines is the automata are abstract models of computer. So abstract models of computer, even that abstract will not be physically exist, it will be theoretically exist. That's all. So why we need this theoretical discussion? Because we will not always expect our result in the physical mode. We supposed to first try to solve the problem in the theoretical mode. If we could get some result, then we can think about the practical mode. Okay. Okay. So with that, the first machine for today's class discussion is finite automata machine. So I think whenever I use the word first machine, then the next moment you also come up with the automata. Whatever we are going to discuss in this particular course is not a single machine. We have a 3 to 4 automaton in line for a discussion. With that, we will start with the primary automaton, a primary theoretical machine. Okay, so first you have to imagine, as I told you, this is also equivalent to a normal computer. In that way, if you have to think, and in that way you have to think. So this memory, this automaton also will have something is called as the computation portion, CPU it has. And this also have a memory, especially for performing the input it has the memory, producing the output also the finite automaton. See, this is very very important, singular word. I have to use the singular, right? Automata is the plural word, automaton is a singular word. So finite automaton is a single machine. If you talk about all the automaton, like finite automaton, stone automaton, Turing machine, then you can be able to use the plural word, automata. Now, if you are discussing about a single machine, then you have to use the singular word automaton. Okay. Now, if you look at that, the facility available in the finite automaton, we have an input and output memory and the processing unit, but we don't have any facility with, there is something is called as a temporary memory. So why I just cross mark this temporary memory? It means generally, if you think about the practical computer, the practical computer will have an input output memory as well as the temporary memory, and along with that there are other features also. But for a theoretical discussion, or the first machine which I wanted to design in theoretical perspective, there I could not have temporary memory facility in my first automaton, that is a finite automata. So what literally the final outcome you're supposed to get from this, it means at the end you can find, with the available capability of the finite automaton, you can able to do only some set of operations only. So what are all those set of operations, what finite automaton can do, what finite automaton cannot do, those things we will discuss one by one. Okay. And before I wanted to discuss much about finite automaton, because that is what our unit number 1 discussion. We have to explore more about finite automaton. I wanted to also tell you the other automatons are in our lineup. We have a push-down automata, as you can see the picture, which is already discussed in the first class. Even though along with the input and output memory, which will also have one more temporary memory is called as a stack. So we have a temporary memory, and the operations the temporary memory will perform, something is called as a stack. Okay. So next, the Turing machine. So there we have an input output memory, as well as we have a temporary memory that too have a facility to access the random access capability. Okay. So this is what the 3 automaton we are going to discuss in our subject. So first I will bring that finite automata. Okay. So whenever you are think about the finite automaton, they consist of input memory and output memory. And whatever the input you are giving, the finite automaton will process and it will produce the output. So how it will process, that we have to discuss later. First, as why I have mentioned the input as a string, that's why in the last class, our third class, we had a discussion for languages. So languages are the collections of strings. So now generally, if you are giving the input to the finite automaton, you have to give the string as input to the finite automaton. So then what else you cannot give? You cannot give a complete language as the input, because for the complete language, what questions you may ask? Generally for a input like a string, single string or single word, you can ask the questions like this is belongs to this particular computation or not, or this belongs to the particular language or not. This is what the general questions we will ask. By the way, the finite automaton will always receive the input in the form of string. The string is nothing but, or where the string will be available, it means string generally available in the languages. That's why in the last class we have discussed about what is meant by languages, or how we have to give or pass the string as the input to the finite automaton. Then what finite automaton will literally produce after computation, it will produce string only. Then you may ask the question whether it will produce directly the string or anything else. For that, I wanted to discuss, I have taken this slide and I will tell you. Generally, you are discussing about finite automaton. The finite automaton will be classified into 2 categories. The first category is called as finite automaton without output. So without output, it means what? You cannot able to get a string as a result. Instead of the string, you will get the answer, whether the string whatever you have given is accepted, or whether the string you have given, whether it is rejected, whether it will be accepted or rejected. Only you will get any one of this answer for given input. Then this type of automaton is called as without output automaton. Okay. And the finite automata will also have another category, that is a finite automata with the output. If you go for a finite automata with the output, then you will get this type of result. Having given input, you will also get an output. Having given string as an input, you will also get a string as output. Here there is no any output. Here you will get the result, either accepted or rejected. No strings are produced. Then this is the one classification of finite automata is called as finite automata without output. So this is the another classification of finite automata. This is called as a finite automata with the output. Okay. So now I can come to this category. If I discuss, is there any other further classifications in that finite automata without output, then we have a 2 sub classified machines to be discussed. The one sub classified machine is called as deterministic D, finite automata, deterministic finite automata. And another classification is non-deterministic finite automata. So this is the one level of discussion, or one part of discussion in our unit number 1. Okay, and this another part of a discussion in our unit number 1 is finite automata with the output. So under this we have a 2 more machine to be discussed. One is Mealy machine, MEALY, Mealy machine. Another one is a Moore machine, MOORE, Moore machine. So these 2 machines are comes under finite automata with the output. So totally in this particular unit number 1, we are going to discuss 4 different machines, and all those 4 different machines comes under the category of finite automata capability. Okay, so what is a finite automata capability? We have an input and output memory, and we don't have any temporary memory. That is the common for all those four machines. Okay, so now we will start explore those machines one by one. How the DFA will look like, how NFA will look like, how melee machine will look like, how Muri machine will look like. We will discuss one by one. So with that, I have my first discussion with respect to this category, finite automata without output. Then I will discuss finite automata with output. This is what the way I have splitted unit number one into two. Two off. Okay. So first, so this is clear. So now I wanted to discuss about this finite automata. Now what I want literally is, I wanted to recollect the thing, one more thing we discussed in the earlier classes. I think I have reserved this space for to discuss the concept of transition graph. I will tell you what is transition graph. Okay, then from this, from this I will continue. Okay, so okay, this is fine. Next, in the first class, before you have to discuss about the concepts of automata theory and formal languages, I told you this is purely the theoretical way of explaining the concept. So for that theoretical explanation, you're supposed to have some mathematical background. With that, on that discussion, on that day class discussion, I told you there are three important mathematical concepts you're supposed to be aware. You're supposed to be well known to handle these situations. I mentioned this word. Now, can someone please unmute your mic and tell me what are all the three important mathematical components I referred in that class? Hello, students. Hello, students. Very good, very good, very good. So I refer something is called as a sets. I refer something is called as a graph. I told you you should have a knowledge of the third thing is called as a tree. I think in the last class, our third class, last class, where we exactly use set, I explained, because there is something is called as a languages that is purely discussed and explained with the basic understanding or basic functionality of set. One point is over. Now we have two more mathematical background in our hand, and we have two more things to be discussed in our hand. So the two things are, one is the machine discussion, or we will call it as automata, and we have the grammar discussion. Now, which mathematical component will help us to, correlate with this graph and tree concept? By the way, next discussion is all about the automata, right? That is, we will call it as a machine. So it will completely rely on the basic principles associated with the concept of graphs. And there is a next component is called as a grammar that is purely rely on the basic mathematical component associated with the concept of trees. Okay, so now I will start discussing this machine with a basic underlying with the graph. Okay, so that's why here, whenever if you want to design your machine, whenever if you want to design your automata, okay, so now it is our responsibility, because it is a theoretical, no, we have to design, we have to do that. So for that we rely on the graph. What generally you have to get the knowledge behind the graph, generally the graph G consists of two components. That is, something is called as a vertices and something is called as a edges. Generally the vertices are represented with this circular pattern, and the edges will always happen between one node to other node. In that category, still the edges will have a two category. One is the edges with the direction, edges without direction. and still in the direction and without direction also, we have a one more component added with these edges, that is unweighted edges and weighted edges. So these are all the basic things you supposed to recollect in order to use those graph features in our automata. Okay, so first, what way in general the automata can be represented. Okay, so now the automata is a thing could be generally represented in terms of graph, and the name of the graph we are referred to represent the automata is called as a transition graph. Okay, and along with that, I also wanted to tell you three more technical keywords. The automaton is purely the theoretical representation of the computer. By the way, it has three ways to represent their machine structure. One way is this transition graph, and the second one is there is something is called as a function way of representing, and the type of function is called as transition function. Okay, and the third way of representing the same graph using something is called as a table. The name of the table is called as transition table. So now what you can come to the conclusion is, whenever if you want to design a finite automata, you have a three options in your hand. So the finite automata can be represented in terms of graph, the finite automata can be represented in terms of function, the finite automata can be represented in terms of table also. Okay, but in general, we will always go with the graph based representation for finite automata, but not only for finite automata, for any automata. It means what? Even for a push-down automata also, we have a transition graph, transition function, transition table. For a Turing machine also, we have a transition graph, transition function, transition table. So this is in general way of representing any theoretical machine. So now this is the one point we come to the conclusion. So now why I am insisting this point, having given problem, if I ask you to design the finite automata theoretical machine, then you have a three options in your hand. Whether you can design the graph for the finite automata, or you can design the function for the finite automata, or also you can design the table for the finite automata. So you have a three options in your hand. So this is what literally I try to convey from this discussion. Okay, so now you have a next level discussion. Finite automata can be represented using these three forms. So first we will discuss the first form is called as a transition graph forms. So what way generally the finite automata will be represented in the transition graph form. Okay, so this is what the representation of finite automata transition graph form. Okay, and we have something, see generally you can see here we have a collection of vertices and we have a collections of edges. So this is seems like what? A normal graph. But the one point is, even we cannot go with this representation as such. Thank you. This representation as such, because along with that basic representation, we have to add some more special features in the finite automata also. Say for example, whenever we are specifying like this, then what about the starting point of this particular arrow? This is the starting point, right? So this is a special type of notation which is dedicatedly used in the transition graph itself. That is the one point. Second, whenever we are representing two times of circle, so where could we find this type of two times circle? Nowhere we could see, right? So this is also a dedicated thing which is specifically used in the transition graph. Then what you may be able to come with the conclusion, you don't think that the basic graph as such we will use. We will use the basic graph. Along with that, we will do some add-ons. With that, the two add-on we will do. The one add-on is this arrow symbol, and the second add-on is this double circle. The first arrow represents the initial state of that particular machine. That is very important. Initial state of the particular machine. Because we know that whenever there is a machine, we are giving the input to the machine not directly. We have a separate memory is called as a input memory. We loaded our input to the input memory. Now we have to take the input from the input memory and start processing. Then where we actually process, what is there inside this machine? Inside the machine we have only this. Only this? No, we have three things can be possible inside this. It may be the transition graph, it may be the transition function, or it may be the transition table. Now, if you think that this is the transition graph is available, then where you have to start processing your input. By the way, the transition graph, we know that it is a graph representation. Generally, whenever there is a graph, we have a collections of node. Then from which node I have to start process? By the way, I have to give some special notation for my start node or initial node. That node will be represented like this. So whenever you can see the node like this followed by this arrow, then this is the representation that this graph will start always like a process from this particular node. So this is what we will call as an initial state. First point. Second, other than this arrow, the nodes which is available in this graph are, we will simply called as states. Simply called as states. Next, from one state to other state, we have seen edges. Fine. Then what is the name of the edges? The edges we are dedicatedly called in this automata as transition. The edges are simply called as what? Transition. So we are not called edges as the word in the automata. We are using the word is called as a transition. Okay. During the transition, what happened between the two states? There is a transition from this state to this state with this edge value. This edge value. Generally, the edge value we will called in this graph with a dedicated keyword or dedicated name is called as input. Next, when we should stop our process, because one of the other way in this picture, upon giving input, we will produce the output. Upon giving input, we will say whether the input is accepted or rejected. Then when I should come to that conclusion, whether I can come to this conclusion or whether I come to this conclusion, when should I do? So that thing will be decided with this symbol. That is, whenever you can see the state with the two circle, the states are we will call as a final state. The states we will call as a final state. So this is what the overall thing you have explored from this transition graph. Okay, then you can test how this transition graph will work. Say for example, you are giving this as an input. Then what is that? Literally the input is simply string. Now you can imagine that previous diagram. Finite automata always receive the input in terms of string. Okay, it will receive the string. Where it will keep their string will be keep always in our input memory. Okay, so each and every cell we have each and every input. By the way, we can keep our input into our input memory. Next, if you take the first input, so A, then we start with the state Q0. Now you have to check upon reading this A from the starting state Q0 where you can go. There are two transitions I could see for this Q0. I have a transition for A as well as I have a transition for B. So upon reading A, I have only option to reach what? Q1. Next, once this input is over, then we have to move our control head to the next input symbol. From the next input symbol, from our current state, we have to check upon reading this particular input where we will reach or where we will make a move. Upon reading this B, I have to make a move to reach the state is called as Q2. As of now, I have covered two input. Next, I will move my control head to the third one and read the third input. And upon reading the third input from the current state, I can reach Q3. The same operation I can do for the next input. Upon reading the next input symbol A, I will reach the state is called as a Q4. After that, I will move my control head and I can find that there is only empty space. Then that is the conclusion that the inputs are over. The inputs are over. There is no any other leftover information in my input memory to read. Once you can come to that conclusion, Then you can come to our transition graph, or we will call it as a automata, or we will call it as our machine. We will come to our machine and check that where we are currently, or which state we are currently. We found that after reading that input, we are in the final state. Then we can come to this conclusion upon giving the given input. After processing my finite automata, I can produce the result as this particular input is accepted by this particular automata. Then I will produce the result as accepted. That's why you can imagine that the output is also string. In terms of the string is only the accept or reject, then that is a without output category. The strings are also produced as like the input string, other than this accept and reject, then that is a with category. Say for example, if you are giving A, B, B, A as an input, you are getting the result also something like a B, B, B. Then you can see here, both belongs to the same type, right? If you get this type of situation, then this is called as finite automata with the output category. And if you see given the input as A, B, B, A, for that you will getting the result as either accepted or rejected, then this is what we will call as without output category. It means we cannot get any output like the same format. We will get only two dedicated result, accept or reject, or we will call it as a Boolean result, one for accept, zero for reject, like that. Okay, in that way you have to imagine this category. Okay, so now this is what we will call as transition graph for what? That is very important question. How to draw this transition graph? So now can you please answer for the question? What would be the influence things to draw this graph? How I have to draw this graph? So I will give you the hint, then you can tell me. If I wanted to draw this graph, I have something is called as a graph in my hand. I have something is called as an input in my hand, and I can produce finally the result as either accept or rejected. Then if I wanted to say this result accept or rejected, then accept of what, reject of what? It means that this particular string A, B, B, A, accept means belongs to. A, B, B, A, not accept, it means not belongs to. Belongs to what or not belongs to what? I need some response from your side. I need some response from your side. Input is there, machine is there. What is the given basic underlying thing I have designed? Why I have designed this machine like this? What is the influence to design this machine like this? What is the input to design the machine like this? After designing the machine only I will test the input. But before designing this machine, based on what I will design this machine? Okay, in this way I will ask. You are giving input is what? String only, right? Where we will actually have a string?
Language.
Okay, so the language will have a collection of string, and even the result also produce what? Whether the string belongs to something or not belongs to something. Belongs to something is nothing but belongs to language or not belongs to language. That's all. Then, if you want to design your automata, then based on what you will design the automata? Based on what questions I will ask you, you will design this automata. So I will give you the question as language. I will give you the question as language. I will give you one language and I ask you to design a finite automata. Then I will take one input from the language, or I will take one string from the language, and I wanted to check whether the input is processed in the automata or not. Now you can completely get the clarity of this automata, because whatever the discussion or the technical keyword I have used, please remember, generally the languages are input for automata. This word I have used. There you can explore two information. Based on the given language only, you can design the automata. and the string available in the language only, you can test the automata. So you can design the automata based on the language. You can test the automata based on the strings in the language. So now I have again used two technical keywords, designing and testing. So for designing, you need a language. For testing, you need a strings in the language. Okay. So this is what the overall understanding. So now you can see here the machines are already constructed. Now what we are going to learn, how we can construct this machine. That I wanted to teach you, how to construct this machine. Okay, so first you have to learn how machines works. Then we will discuss how we will design the machine, because two things are there. Here we will did only testing. That's why here I have written two keywords. We have to test the machine. Which machine we tested? Automata machine we tested. But before you have to test, so okay, how did you test? Based on the string, where the string is available in the languages. Before testing, you have to design no first. Designing is also with your responsibility. How to design? Based on the language you can design. So first you have to design the automata, then you have to test the automata. So for designing you need a language. So how to design we will see. So now first we will test how machine works, then we will think about how to design the machine. Next, so the same scenario, having given input, you cannot directly process the input, keep the input in our input memory, and we have something is called as a look ahead pointer. LOOK, look ahead, AHEAD, look ahead pointer. So this is the pointer will help us to get a confirmation that whether the input symbols in the strings are completed, or we read all the inputs or not. So now you may be come up with a one more keyword during my discussion, symbols, right? So the symbols, later I previously I used the word is called as a letter. Okay, so now you need to get a clarity for this. Generally, whenever if you want to form the collections of strings inside the language, you need basic alphabet. Okay, so the basic alphabet will be generally available here. The basic alphabet sigma is A and B. So based on this alphabet, you can form your string. Once you form a string, say for example, you form a string is called as a triple A. Then yes, we have a collections of, based on this alphabet only you form the string. Okay, so now the string consists of what? Collections of letters. The other word I can call each and every letter is called as symbols. The other word I can call each and every letter in the string is called as symbols. So in what way I can define is, strings are collections of symbols and languages are collections of strings. That's all. So now I have introduced one more technical keyword that is dedicatedly used in this particular topic, that is symbols. Okay, so now this look ahead pointer will help us to give a confirmation that whether the input symbols are in the input memory, what are all the input symbols are read as of now. So with that, if you found that the control head is in the left hand side of the complete input string, then this is the confirmation that none of the inputs are read. Once you been there in this state, and upon reading this input A, then if you make a move to Q1, then the control head also will be there in that position. Okay, so now next you can read this one, the control head will be like this. Next you are moving the next input, the control head is pointing here and you are making the transition here. And next the control head will be here and you are making the transition. Next the control head will be here, then this is the confirmation that I read all the input. Okay, now you can see there is a transition of the control head, there is a color also. Okay, so what is that meaning? Say for example, here the control head is pointing here, and wherever it is pointed, that movement I have already done. Then what generally the control head is? The control head is the confirmation that, or it will pointed to the position and from that position, what are all the input available in the left hand side? Those inputs are already processed. So whenever if it is pointing to this, then that also in process. The things which is available in the left hand side are all processed. So in what way you can understand this? If you see or if you watch a cricket match, always you can see the score and the number of over. So you can see the over detail, right? The over information is all about the past information. What are all the things completed as of now? What is not the current state? The same way, the pointing to this, it means these inputs are already completed. The pointing this it means these inputs are already completed. Pointing this, it means these inputs are already completed. Okay, so this is currently going and these are all already completed. Okay, and after reading the empty space, then it will come to the conclusion that the things which is available in the left hand side of the look ahead pointers are completely read. Once that situation we faced, then we can check which state we are in the transition graph. We are in the final state, then we will produce the result as yes, the input string is accepted. So where this input string is available in the language. Okay, then we can come to the conclusion that this particular input string A, B, B, A, we will assign to one word is called as W. Now we can say the W belongs to this language. This is the final result we will write. Because it is a theoretical subject, no, theoretical way of explaining the computation, no, then we have to use some mathematical notation to give our result. So this is what the way the two lines will give the result after we perform the computation. So this is only the accepted scenario. What about the rejected scenario? Same procedure. Start with the starting state upon reading the input A where you are in Q1. After reading the next input where you are in Q2. After reading the third input where you are in Q5. After reading the empty space, you have to confirm that which state you are. If you are find that you are in the state which is not double circle, then that is the state are not considered as the accepting state or final state. That is a non-final state. So out of this picture, there are three important components are there. This is the initial state, this is the final state, and other states are generally called as non-final state or non-initial state. So these states are not initial state as well as these states are not final state also. Okay, after reading your input, you have to be there in only in the final state that will be identified by two double circle. Only for that scenario or only for that picture, I can come to the conclusion is the input is accepted. After reading this scenario, if I will be there in the state where there is no double circle, then I can come to the conclusion is that this is the non-final state. Here, so this is what the way the finite automata machine works. Okay, so now we will see more example. So this is the one machine, right? So with the one machine, we tested the accept and rejected scenario. Now we will see the other machine. See, I already told you there are two things we are going to learn from this. First, we have to design the machine, then we have to test the machine. For a designing, we need a language. For a testing, we need a string. So first, right now, we have to complete this portion. So we will test the already designed automata with a string. Then I will teach you how to design the automata using the languages. That's why again I will tell you the languages are input for the machines or input for the automata. Okay, and the same thing I will also tell you the languages are again the input for grammar also. Okay, and here I wanted to tell you one more word. The theoretical discussion, I dedicatedly assigned two technical keywords for this machine and grammar, right? The automata are generally called as acceptor and the grammar are generally called as generator or generators. I didn't know till what is how the generation will be done because we are not discussed now, that is fine. But now we can come to the conclusion why the automata are called as acceptor, because finally it produces some process and saying that accept or reject, no, that's why the automata we will call as acceptor. The dedicated we have called the automata are called as acceptor. Okay, so now we can look at this machine, this automata. So this is again what automata I can say, this is the finite automata. So in what way, again you may ask, sir, you said The transition graph is a kind of representing the all automata, not only finite automata. Then how can I get to the confirmation that this is also look like a transition graph? Definitely you said for all the transition graph will have a same structure. Yes, I didn't say, now I'll say all the transition graph will have a same structure. In what way I can identify that the automata or the finite automata graph, or the automata or the push-down automata graph, or the automata or the Turing machine graph? In what way I can identify, sir? How could I identify the difference? By the way it will represent the starting state, the way it will represent the final state, there is no difference among other transition graphs. We have a difference only with this label information, or we will call this edge information, or we will call this transition input information. So the way we are specifying the finite automata label are completely differ in the way we are specifying the label information in the push-down automata. The way we are referring or specifying the push-down automata label will completely differ from the Turing machine. By the way, at the end of unit number 5, you could get the clarity of how those machines are differ in their representation, even though they will simply call as a transition graph. But each and every graph of a particular machine will have a different structure, especially the structure that are associated with the label information. So that clarity you will get once we will end unit number 5. Okay, so now you can see this picture. So the second machine. Now you can see, okay, the label informations are fine. Previously in the example, each and every transition, see here, you can see the Q0, upon reading the input, I will be there in Q1, fine. From Q0, I can see also one more thing like this. This is already still available in the graph itself. This is what we will call as a self loop. After reading this input, I will be there in my same state. Then this is what we will call as a self loop. So in the finite automata, even we have the representation of self loop also. 1 point. Second, the previous diagram I can see in the edge there is only one symbol, but in this diagram I can see two symbols, that two separated with a comma. Then what is that meaning? It means from Q1 reading A, I have only option to go Q2 only. From Q1 reading B, I have only option to go Q2 only. Then what way I can represent this diagram? I can represent this diagram by separate edges also. From Q1 I can go to Q2 by A. From Q1 I can go to Q2 by B. This is also you can represent. The other way you can represent the same situation is using this comma. Then what the meaning of the comma? The comma is nothing but OR operation. What is this? This is a horizontal, vertical line, right? So we will call it as a vertical bar. This is the representation of this comma. It means whether I can prefer either A or I can prefer either B. Then what is that meaning? How I can able to even rewrite this A comma B? See, for example, this A and B can be write like this. Even this can be write like this also, A or B. Or even this can be write A plus B also. Here the plus represented that OR operation. Now what is your final conclusion? Whether whenever you can see in the diagram A comma B or A or B or A plus B, all will give the same meaning of this A and B. So this things itself could be represented in 3 different notations. Though these are all simply we will call it as notations. Okay, so this is what the new things which we have explored from this graph. Other than that, definitely there should be a starting state, definitely there should be an ending state. Now you may ask one more question. We have only one ending state is possible? Then the answer is no. There is no any restrictions with the number of ending state. But we have restrictions with number of starting state. We have only one starting state is possible, and we have there is no restriction about the number of ending state. Okay, so these two are the further clarity you supposed to have from this picture, or we will call this from this graph. Okay, so now again we will test the graph. You can see here again From Q2, we have a two option. Upon reading A, you will be there in Q2 itself. Upon reading B, you will be there in Q2 itself. But at a time, you are eligible to read only one input, not both the input at the same time. Then what is your understanding? The input memory also, we have a set of cell. Each and every cell will have a capability to occupy only one input symbol at a time. Now that's why I have to use the word symbol. Only one symbol at a time. So now you can see reading input A will be there from Q0, you will be there in Q0 itself. After reading the second A, where you will be, again I will be there in the Q0 only. Reading first A, reading second A, I will be there in Q0 only. Because I don't have any transition from Q0, reading A to other state. And reading the input B, I will be there to reach Q2. Then after B, I have to check, I can see only the empty space. Then I can come to the conclusion is that I have completed to read all the input symbols. Then I can check which state I am. I can find that the state will consist with the final state symbol. Then I can come to the conclusion is that this input string is accepted by this automata. Then you may ask the question, generally we will build the automata for what? We will build the automata for languages. So the languages only we are build the automata. Then what are the type of automata we are discussing? Finite automata. Generally the language will have a finite automata. Then those languages are we will generally call as regular languages. Sir, why you are using the regular as a word in front of the languages? That's why again you can recap. For a machine, we don't have a single machine. We have a finite automata machine, push-down automata machine, and Turing machine. Likewise, for the languages also, we don't have a single language. We have a regular language, we have a context-free language, and we have a context-sensitive language, and we have a recursively enumerable language. Likewise, whenever we can see something is called as a language, it's a collection of string, and for those language, I can able to design the finite automata. Then I can call those languages are regular languages. Then what is that meaning? Whenever the language is regular language, then definitely we have a finite automata for it. That is a final conclusion. Whenever the language is regular language, definitely we have a finite automata for it. Then which languages are called the regular language? In the reverse, you can say, what are all the language, there is a finite automata for any language, then this language I can call it as a regular language. Okay. So, why do we have other classifications? We will discuss. Because in the regular languages also, we have some restrictions, or for some of the languages are not regular, then for those languages, literally the conclusion is we cannot design finite automata. We cannot design finite automata for some languages. Then those languages I cannot call as the regular languages. Then for the languages, I have to try to design some other machine. Then say for example, the push-down automata can be designed for that machine. Then I can call those languages are context-free languages, not the regular languages. Then what is the understanding of this? The regular language, we can design finite automata. But for a context-free language, we cannot design the finite automata. For a context-free language, we can design only push-down automata. So likewise, we have an interrelationship between all the languages and all the machines. That we will discuss later on. One by one, we are going. Then only you can get the relationship between all three components. Generally, no need to get a confusion. We have a relationship with only three components: language, automata, grammar. That's all about the whole subject. I will give you the enough clarity at the end, because once you go with the progress, at the end you will get the relationship among them. Now you can see the rejection scenario. There is an input, the same automata you can take. Upon reading B, you will be there in Q1. Upon reading A, you will be there in Q2. Upon reading B, you will be there in Q2 itself. After reading all the input, you can check which state you are. If it is not final state, then definitely this input string is not accepted by this automata. Then if this input string is not accepted by this automata, then definitely this string is also not belongs to this particular language. Then this input string is not the part of the language. So in what way we are using this automata for this picture? We are testing a given string is belongs to this language or not. That's all. That is the overall objective. So that is the task given to us. The task given to us, given a string is belongs to this group or not. That is the task they are given to us. That task, that computation, that problem, I will solve this. Okay, sir, the computer can solve an infinite problem. Okay, but always the initial state, the computer designed with solving the basic problem only. No, so here also I will start in that way. Okay, so now this is the time you have other class, and I will conclude the discussion of this with this moment, and I will continue the discussion of this with afternoon class. Now the time is 9:51. The representative, please take the attendance for today's class, and after completion of this week, please share as you did for the last week.